Hello, this is Praveen Kumar. My branch is mechanical engineering. My topic is neural network control of automative fuel injection system. So first we have to know the neural network control of automative fuel injection system. So a neural network methodology is developed for air to fuel AF ratio control of automative fuel injection. The dynamics of internal combustion engines and fuel engine systems are extremely non-linear, impeding methodical application of control theories. Thus, the design of standard production controllers relies heavily upon calibration and lookup tables. A neural network type control is developed in this neural network control of automatic fuel injection system scale for its function, approximation abilities, and its learning adaptive capabilities. A cerebellar model articulation control neural network is implemented in a research automobile to demonstrate the flexibility of this control architecture. Experimental results shown that the CMAC fuel injection control is very effective in learning the engine non-linearities in dealing with the significant time delays inherent in engine sensors. So minimizing emissions. The objective of a fuel injection controller is to maintain the air fuel ABF ratio at value desirable for drivability and emission minimization. It depicts the efficiency of catalytic converter for oxides of nitrogen, hydrocarbons, and carbon monoxide for maximization of efficiency and thus minimization of harmful emissions. The desirable ABF ratio is stoichiometric mass ratio, which is taken as 14.65:1. In the past, the performance of the production engine control module has been sufficient to pass all government mandated emissions standards and to provide adequate drive fuel. However, recent legislation will soon require a much cleaner engine. By the year 2003, laws such as will soon require a much cleaner engine by the year 2003, such as the 1988 California Clean Air Act require 110% of manufacturers' fleet to be zero emission vehicles. An 84% decrease in HC emissions, a 74% decrease in NQI output, and a 60% reduction in CO production for the entire fleet. These regulations will soon require extensive improvements to the current fuel injection controls. The standard ECM controller is based on a proportional plus integral type model with a large array of varying gains stored in a lookup table generated from the calibration and tuning laws. So this method for fuel injection system was proposed and experiment demonstrated a neural network method is used in the fuel. So the standard ECM control is based on the proportional plus integral type model with a large array of varying gains stored in a lookup table generating from calibration and tuning process. So the neural network method for fuel injection system is proposed in the article as an alternative. The CMS neural network was selected for its efficient computation and fast learning. In this article, the feasibility and potential for CMAC to control fuel injection system is real-time or demonstrated using a research automobile. So this is the CMAC fuel injection control. Any engine state is well described by the manifold pressure, load, and the engine speed. Detailed engine model used in the article can be found, and for brevity is not repeated here. The two inputs were chosen from the CMS. The CMS neural network can be implemented very efficiently. Each of the two inputs index one dimension of a three-dimensional memory space. The third dimension corresponds to the C layers of repetitive fields and provides the generalization. A mapping of the first input is achieved as follows, where I indexes each for the C layers. This is the formula. In the above, I denotes the layer, div is integer division, and u1 is quantized index of maximum value size, whereas 1 is the physical memory size in the first dimension. Thus, the quantization width is generalization versus performances. To learn online The CMS requires feedback from ABF ratio sensor. Production vehicles use an oxygen sensor with a switching output about the desired stoichiometry ABF ratio. Linear ABF ratio sensors are commercially available for laboratories, but the cost of such sensors in the present technology is prohibitive for production use. So in this article, that use of a linear ABF sensor for the initial CMSC learning is considered due to the exponents of the linear sensor. Its usage will be confined to the laboratory where a single network will be trained for the installation in the production. Right. The O2 sensor based learning algorithm can be activated post graduate production. Since the CMS can be well trained initially, a low learning rate can maintain stoichiometric ABF ratio control over the life of the vehicles as the engine dynamics change due to age. In addition, research is underway for a CMS based controller which only utilizes the production O2 sensor. The results will be reported later. In order to reduce the training time of the CMS, the weight space is initialized with generic values derived from the model. Based on this model, the desired mass rate of fuel to command FLD for a stoichiometric ratio. The formula is the formula of stoichiometric. So this is the table of characteristic of binary oxygen sensor. Air to fuel ratio is the output V, and rich learn, where C1 is the physical constant, QVO is the volumetric efficiency, MA is the mass of air intake manifold. We see the engine speed and the stoichiometric ABF ratio. Since MA cannot be directly measured, the ideal gas law is used to produce an expression for the desired fuel command rate as function of PM, the manifold pressure, the TM, the manifold temperature, and the gas constant for air R. In 11 has been expressed the terms of the engine displacement V and the cylindrical geometry through the manifold temperature appears directly. It is not needed as an input CMS since it remains relatively constant. However, TM is used as an input to the control system. A temperature dependent set of linear correlations between O2 sensor output and linear ABF sensor output, as in figure 4, has been determined to allow the CMS to utilize the same learning routine for both linear ABF sensor and O2 sensor. So initially CMS is trained using with generic model for Q0. If the volumetric efficiency were known, for the expression would provide the exact command for the stoichiometric ABF ratio. Other variables 11 are either known or measured using production sensors. However, QV0 cannot be modeled analytically. In fact, this model serves only to initialize the CMS weight space since it contains large errors, so resulting in poor performances. To improve the CMS performance, the weights need to be accurately adjusted to learn in real time. Linear ABF ratio sensor is used for feedback to learn and adjust weights in real time. So due to the downstream location ABF sensor ratio exact manifold, the feedback is significantly delayed. CMS weight update law is developed from this application. Since the delayed responses to the old command is known to be the current ABF ratio reading from the sensor can be expressed by substituting stoichio. Thus this the formulas, this 12th and 13th are the formulas. This algebraic manipulation yields the desired change in mass rate of fuel command in the whole state. So substituting 13 for in 8 provides a general learning algorithm for the CMS. This specifies incremental change in weight activated during the command so that the next time that the same combination of engine states is achieved. So the new more desirable command will occur. Conventional control methodologies cannot easily deal with time delays. So the CMS can easily compensate for the delayed information, storing past ABF ratio response in a time dimension of receptive field arrays as discussed above. This is one of the major advantages of the CMS based new fuel injection control method developed. However, this task is complicated by the dependency of the magnitude of the time delay upon the both manifold pressure and the engine speed. Since the dynamics of the exhaust manifold are complex, an empirical calibration was used to relate the time delay magnitude to manifold pressure. In turn, allowing the current ABF reading to modify the CMSC weights from several engine revolutions previous. So experimental results. CMSC neural network control has been implemented on the 1988 Oldsmobile Calasis with a quad 4 double overhead cam 4-cylinder engine. The Calasis is equipped with two 3x-based portable Dolch microcomputers. The Dolch computers contain RTI-15 input-output boards of the data acquisition and control. One computer receives input voltage from the throat position sensor TPS and commands to the throttle actuator. For drive-by-wire testing, the CMSC control is implemented on the second computer, which collects engine data and executes the CMSC control routine each engine revolution. A photograph of the test vehicle is shown in this figure. The control objective is to maintain a stoichiometric ABF ratio with deviations limited to the maximum of F1%. The straightened control requirement is derived from the degradation of the catalytic converter efficiency by as much as 50% of the deviation from stoichiometry of 1%. So thus the control will maximize the catalytic converter efficiency and thereby meet emission standards. The CMS fuel injection controller has been assessed on to driving scenarios. All the appropriate efforts were made to assure. So each control evaluation after initializing the CMS weight space with the generic model of the volumetric efficiency using testing of each scenario proceeded linearly and independently with learning on all trials. So this is the picture of the test vehicles. So the data were collected with the test vehicle in a drive automatic transmission as it would like be operated under normal driving conditions. All testing has utilized the linear ABF sensor. Future work will address the usage of the O2 sensor routines. The results demonstrate the ability of CMS to maintain stoichiometric ABF ratio in a controlled environment. The first test involves the car slowly accelerating from a stop. As seen in figure 6, the desired F1 boundaries, the expectation reach 12.4 ABF ratio peak for the whole 9.1 minus to 14.9 seconds per period. This perturbation is difficult for us to explain but occurred frequently during ECM. So this is the ECM control on first scenario. This is the figure ABF ratio of the ECM control on first scenario. And this is another figure of CMSC control on first scenario. The performance of the CMS control with the linear ABF sensor is depicted. The boundary for the entire duration of the test, the CMS performance is better than the ECM in this test since the performance of CMS is now acceptable for this test. So the learning may now be halted with this fixed set of the weights and without further learning. CMS will continue to achieve same good results on more trials of the same test. Thus, when the CMS has been fully trained to produce stoichiometric ABF ratio control over a large set of possible engine states, the feedback from the ABF sensor is no longer necessary and the CMS could perform open loop control with acceptable results. So demonstrate the ability of the CMS to learn stoichiometric control over a difficult scenario. The double tip over driving test shown in the figure 8 evaluate the performance of the CCM control is shown figure 9. The tip at t equal to 6.0 seconds. The ECM has lean spike of a magnitude ABF ratio 17.1. This learn region leads to the rough acceleration. This occurs again the second tip at 18.0 seconds. The ECM is able to maintain the ABF ratio within the F1 boundaries only during the first steady state region from 0 to 6 seconds, even during the quasi steady state conditions. So the poor performance displayed in figure 9 was recorded contemporaneously with the following CMS results and will therefore be used as a standard comparison. So this is the figure 8 second throttle scenario. Throttle angle decrease time seconds. So this is the ECM control on second scenario. So this figure 10 shows the performance of the CMS fuel injection control during the open loop control only after training by the generic expression for the volumetric efficiency. The performance is very poor. However, the 4 iterations of the linear ABF sensor learning routine at a learning rate of phi equal to 0.5. The performance is improved to that shown in the figure 11. CMS control ABF ratio goes run briefly at tip in and more significantly reach at tip out. Other than during these short periods, nearly stoichiometry is achieved. The performance improvement is drastic and in general much better than the production ECM control. This is the open loop CMS control on second scenario. This is the CMS control on second scenario, fourth trial. So these two limited testing scenarios have demonstrated that with the linear ABF ratios in sensor learning routine. So CMS based control is capable of improving upon the performance of ECM control over a certain band of manifold pressures and engine speeds. So it is expected that with the training over a suitably generic set of inputs, the CMS will be able to maintain nearly stoichiometric ABF ratio over all the driving conditions. So performance should be adequate even without further learning, so that the trained CMS could be used in open loop control without further online learning. The use of the binary ABF ratio sensor need not necessarily be implemented to be regulate performance. So the conclusion is, by finally we have learned a CMS neural network controller has been designed for fuel injection systems and implemented in a laboratory test vehicle. It is designed CMS control is very computationally efficient and therefore suitable for real-time implementation. While only the expensive linear ABF ratio sensor learning routine was implemented, the result demonstrates the CMS control has excellent potential for good emissions performance. The continuation of reported work shows the CMS method can be effectively implemented in production vehicles with only the standard binary AF sensor. The result will be reported later. Thank you.